Hi there, Mr. Sutton here, bringing you the AB Calculus 5.8 classwork solutions on FTC derivatives of integrals. For this problem, we're trying to take the derivative of this integral with an upper limit of x. Since we're taking the derivative of an integral with an unknown upper limit, we basically just plug the upper limit into the dummy variable in here. So this is just going to be the square root of 1 plus x squared. And we would multiply by the derivative of x using the chain rule, but the derivative is just 1, so this is actually the final answer, choice C. On this problem, I've got a function defined as the integral from 0 to x cubed of this trig function, and I'm trying to find f prime of radical pi. So since I'm taking essentially the derivative of an integral with a variable in the upper limit, I'm going to substitute the upper limit in for the dummy variable, and then I'll have a chain rule in there as well. So I'm just going to get rid of my integral, and I'm going to have cosine of x cubed squared. But now I have to apply the chain rule on x cubed. So I'm multiplying by 3x squared. And just cleaning this up a little bit, this is 3x squared times cosine of x to the 6th. Now let me go ahead and plug in radical pi for all that. So that's 3 times radical pi squared times cosine of radical pi to the 6th. This is going to be just 3 times pi out in front. And in here, I'm going to have the cosine of, let's see, this is going to be pi cubed if I do 6 times 1/2 for the exponent. And that's actually one of the answer choices, choice D. On this question, they want to know the antiderivative of radical 1 plus x cubed. Now, this is a tough antiderivative to take by itself. We really don't have a good technique for it. However, what we can do, since they gave us all these answer choices, is just start taking derivatives of these until we end up with the original expression. And let's just hope it doesn't take too long, right? So let's start with choice A. This is an easy one. We're just using the power rule. So this is 3/2 times 2/3, which cancels out, leaving us with just 1 plus x cubed to the, we have to subtract 1/2 power. And that's awesome because that's the square root of 1 plus x cubed. However, we also have to multiply by this inner function's derivative of 3x squared. So that is not what we're actually looking for. Now, it'd be nice if we could do all this and just divide by 3x squared, which kind of looks like answer choice B. But answer choice B is going to actually require the quotient rule to do all this stuff. So we're going to hold off on testing this one out, till after we try these other choices. All right, so choice C. Now we're taking the derivative of an integral. So we're just going to plug the upper limit into the dummy variable. So we've got the square root of 1 plus x cubed, but we have to multiply by the tail of this, which is 3x squared. And that does not match what we started with up here. This one, we're just plugging in x cubed for the t here. So I've got 1 plus x cubed, but again, I've got a 3x squared tail to multiply by. So those are both no's for C and D. All right, so now we go on to E. We're just plugging in the upper limit again. That's the square root of 1 plus x squared now. However, there's no tail. There's a tail of 1 if you take the derivative of x. But this is it. There's nothing else to do on this one. So we don't really need to check out choice B because E is it. For this problem, I've got this g function here, this integral function with a sine of t squared inside. I want to know on which interval g is decreasing. So to help me get that, I want to figure out what my g prime is. And I'm just taking the derivative of an integral. So I'm just going to plug my upper limit into the dummy variable. So that's going to be just sine of x squared. So now I'm just going to graph this out. And since I want to know where the original function is decreasing, I'm just looking for places where its derivative, g prime, is below the x-axis. I'm going to do this on my graphing calculator since this is a calculator question. So here I am in my y equals. I have sine of x squared in there. And let's see here. I'm going to go to window and make sure I'm going from -1 to 3 because that's the interval they said to graph it on. I'll do a zoom fit for this. Guaranteed to get the perfect window for this function between -1 and 3. And I can see there's only one place in between here where we're dipping below the x-axis. So I'm going to do second trace, and let's figure out what the zeros are there. So over here on the left, we've got, let's see, click there once, click again a little bit past it, enter for one more time for good measure. That's about 1.772 right there. And I'm just going to quickly do an alpha trace 0 call again. So now I'm trying to find this 0 over here. So I'm going to move a little past it, press enter a third time, and now this is going to be about 2.507. So here's what it looked like on my grapher, more or less. And then from 1.772 to 2.507 is where the original function g is decreasing. So that gives us answer choice D. For this problem, we want the derivative of this integral. So since I'm taking the derivative of an integral with a variable in the upper limit, I'm going to replace the t in here with my upper limit variable. So I'm going to write sine of x squared cubed. But now since x squared has a tail that's not just 1, I have to use my chain rule and multiply by 2x. And then cleaning this up, this is just going to be sine of x to the 6th with a 2x out in front, which is going to give me answer choice E. For this problem, I'm trying to take the derivative of this integral right here. Since I'm taking the derivative of an integral, I'm going to cancel out the integral and just plug in this upper limit for my dummy variable inside the integrand. So I'm going to write ln of 2x, the whole thing cubed, plus 1. But since 2x has a tail that's not just 1, I have to multiply by my chain rule here. So multiplying this by 2. And now if I just simplify that a little bit, I'm going to have 2 times ln of, this is going to be 8x cubed plus 1 inside the ln. And that's going to give me answer choice D. For this problem, I'm trying to find the limit as x approaches 1 of this crazy expression here. So I'm going to take the limit of these individually. I've got a sneaking suspicion that this is one of those L'Hopital's problems where I'm reading at 0 on the top and the bottom. But let's play it out here. So if I plug 1 in for the x up here, I've got the limit as x approaches 1 of all this. I'm plugging 1 in here. That's going to give me an empty integral. So I just have an area of 0 that this is approaching. And if I plug 1 into the x squared minus 1, well, that's 1 squared minus 1, which is also 0. So it turns out these things both come out to 0 as x approaches 1, which means we can use L'Hopital's rule, just as we suspected. So now I'm going to write my limit again, and I'm now going to take the derivative of the numerator and the denominator separately. For the numerator, I'm taking the derivative of this integral, so essentially just plugging x in for the dummy variable here. So this is e to the x squared for my numerator. And for the denominator, we're going to have 2x, and then the 1's going away because it's a constant. So if I plug 1 in again, I'm not going to get 0 in both places at least. So I'm probably going to get some kind of answer. That's going to be e to the 1 squared over 2 times 1. So that's just e over 2, which gives me answer choice C. On this problem, we have some function f that we have a whole bunch of information about in this table. And just kind of skipping ahead here, we have some g function that is the integral from 1 to x of f of t. So basically what we're trying to do on this part of the problem is figure out all the places where g has relative maxes and mins and determine which one it is with a justification. If I want to know where g has a relative max or min, I need to know a little bit about g prime. And g prime, as it happens, if we take the derivative of this equation here, g prime is just going to be f of x, because we're just plugging the upper limit into the dummy variable. Okay, so we need to look at f of x and see where that's changing sign. Well, it just so happens this table has all sorts of information about f of x. So let's just look for a place where f of x equals 0. We move over here to x equals 1. So if we look here, we see that f is changing from negative to positive at x equals 1. That means that g is going to have a relative min there since you're going from negative to positive. And now if we keep looking in the f row here, we see that f equals 0 at the x value 3, where we are changing from positive to negative. That means that we're going to have a relative max at x equals 3 for the g function. For this problem, for the function g defined in part C, we want to find all the values at which the graph of g has a point of inflection and justify the answer. So if we want to know about points of inflection for g, then it would be helpful if we knew about g double prime. Now, another way to get at this is to see where g prime is switching from increasing to decreasing or decreasing to increasing. But they didn't really give us that in the table. They actually gave values of things that were positive or negative. So we're just going to go with g double prime to show the inflection points this time around. If we saw on the last part of the problem that f was really g prime, that means that g double prime must be f prime. And now we're going to look at the f prime row here. We see that we are changing from positive to positive at x equals 1. That's not going to be an inflection point because we don't have a change in the sign of g double prime. But over here at x equals 2, we're changing from positive to negative. And we're changing negative to negative at x equals 3, so that doesn't help. But right here, where we change from positive to negative, since f prime or g double prime is changing from positive to negative here, that means we're going to have a point of inflection at x equals 2. For this problem, we're trying to take the derivative of the integral from 0 to x cubed of this stuff. Since I'm taking derivative of an integral, I'm just going to plug my upper limit into the dummy variable and use my chain rule here. So I'm going to write just ln of x cubed squared plus 1. But now I have to multiply by the derivative of x cubed, which is 3x squared. Cleaning this up a little bit, I can write this as 3x squared times the ln of x to the 6th plus 1. And that's going to give me answer choice E. For this problem, I'm trying to find the f prime of 2 here, where f is this integral function. Since I'm taking the derivative of this integral, I'm just going to plug this upper limit of 2x in for all the t's. So I've got square root of 2x squared minus 2x. But don't forget to multiply by the derivative of 2x, which is 2, because we're using the chain rule here. Next, I could simplify this a little bit, or honestly, I can just go straight ahead and plug in 2. I think I'm just going to do that. So I'm going to have 2 times the square root of 2 times 2 squared minus 2 times 2. Whole lot of 2's in here. Let's take a look at what's going on in the inside here. So 2 times 2 is 4. Square that, and I have 16. Minus 4 over here is 12. So 2 radical 12. And is that one of the answer choices? It is, E. So we don't have to keep simplifying. We're just going to call it a day here.